You've seen stars. Of course you have. You walk outside on a clear night, you look up, and there they are. Thousands of them. You point at one and say, "I see that star." And you are absolutely, completely wrong. You have never seen a star. Not once. Not ever. And by the time we are done here, you will not be able to look at the night sky the same way again. Because what your eyes actually do when you look at a star is so much stranger, so much more indirect, so much more astonishing than you think, that the word see barely applies at all. But let me not get ahead of myself. Let me start where everyone starts. Let me start with the obvious. Light leaves a star, it travels across space, it enters your eye. Your brain builds an image. You see the star. Simple, clean, direct. That is what they teach you. That is what feels true. And every single step of that story has a problem. Let us begin with the first one. When did that light leave? Take the star Vega. Lovely star, bright. Easy to find. One of the first things you notice in the summer sky if you are in the northern hemisphere. The light you see from Vega tonight left that star about 25 years ago. 25 years. That means you are not seeing Vega as it is. You are seeing Vega as it was when you were, what, a child? A teenager? A different person entirely. The star you are looking at is a ghost. A time-delayed postcard from a place you will never visit. And Vega is close. It is practically a neighbor. Betelgeuse, the bright reddish star in Orion's shoulder. That light has been traveling for about 700 years. You are seeing Betelgeuse as it was during the Middle Ages. The Andromeda Galaxy, which you can see with your naked eye on a dark night, that light left over 2 million years ago. 2 million years. Your species barely existed. Homo erectus was wandering around Africa. You look up and you see light that has been traveling since before your species knew how to talk, before your species knew how to think the way you think now. So right away the word see is in trouble. You do not see the star. You see what the star was doing a long time ago. And there is no way around this. You cannot speed up the light. Nothing travels faster. This delay is not a limitation of your equipment or your eyes. It is a limitation of reality. But all right, fine, you might say. That is just a technicality. The light still comes from the star. I still detect it. I still see something real. Fair enough. But before we even get to the light itself, let us think about what happened before the photon left the star. Because that part of the story is wild, and almost nobody talks about it. The light you see from a star was not made at the surface. It was made deep in the core, where the temperatures reach 15 million degrees or more, where the pressure is so enormous that atomic nuclei slam together and fuse. That is where the energy comes from. Nuclear fusion. Protons smashing into other protons so hard they stick together and release energy. But the photon that gets born in that furnace does not just zip out of the star like a bullet leaving a gun. The interior of a star is incredibly dense. A photon produced in the core travels less than a centimeter before it hits another particle and gets absorbed. Then that particle re-emits a photon which travels another fraction of a centimeter and hits something else. The photon takes what physicists call a random walk. It staggers around inside the star, bouncing in random directions, absorbed and re-emitted over and over and over. How long does this take? For our sun, the best calculations suggest somewhere between 10,000 and 170,000 years. A photon born in the core of the sun today will not reach the surface for something like 100,000 years. It will bounce trillions of times, taking a drunkard's walk through a sea of plasma before it finally reaches the outer layer and escapes into space. And by then it is not the same photon anymore. Not really. It has been absorbed and re-emitted so many times that calling it the same photon is like calling a ship that has had every plank replace the same ship. The gamma ray born in the core has been degraded step by step into lower energy photons. By the time something escapes from the surface, it is mostly visible light and infrared. The star has chewed up its own radiation and spit it out as something gentler. So the light that reaches your eye is not just old in the sense of travel time through space. It is old in the sense that the energy behind it was generated eons before it even started its interstellar journey. The starlight you see tonight carries energy that might have been produced when woolly mammoths still walked the earth, even before it left the star. All right, now let us look at the light itself. All right, and let us look carefully because this is where the story starts to crack open. What is light? You know the standard answer. It is an electromagnetic wave. It has a wavelength, a frequency. It moves at about 186,000 miles per second through vacuum. Your eye is sensitive to a tiny sliver of the electromagnetic spectrum, roughly from about 380 nanometers to about 700 nanometers. That is visible light. Everything else, the radio waves, the microwaves, the infrared, the ultraviolet, the X-rays, the gamma rays, all of that is invisible to you. Completely invisible, as if it does not exist. But it does exist, and there is a lot of it. A star does not just emit visible light. A star emits across the entire electromagnetic spectrum. It is screaming in radio. It is blazing in ultraviolet. It is whispering in infrared. It is shouting in X-rays. And your eye picks up this tiny, tiny fraction, this laughably narrow window, and says, yep, I see it. Let me put this in proportion. The electromagnetic spectrum spans wavelengths from less than a trillionth of a meter to more than 1,000 kilometers. The part you can see covers a range of roughly 320 nanometers. If you stretch the full electromagnetic spectrum across a line from here to Los Angeles, maybe 3,000 miles, the visible part would be a strip the width of a pencil line, maybe thinner. That is how much of the star's output you are detecting. Imagine you are standing outside a concert hall. A full orchestra is playing inside. Beethoven. Every instrument, every section, the full glory of the thing. And you are listening through a keyhole, a very small keyhole. And through that keyhole, you can hear, let us say, the second violin. Just the second violin. Not the cellos, not the brass, not the timpani, not the woodwinds. Just one instrument out of dozens. You would walk away and say, I heard the concert. Did you? You heard a sliver. A narrow filtered slice. That is what your eye does with starlight. You catch the second violin and you call it the symphony. And by the way, that keyhole is not even transparent. It has its own distortions, but we will get to that. Even within the visible range, your eye has preferences. It is more sensitive to some wavelengths than others. The peak sensitivity of the human eye in bright light is around 555 nanometers. That is green-yellow light. Your eye is literally built to be best at detecting the kind of light the sun puts out most strongly, which makes sense from an evolutionary standpoint, but it means your sensitivity curve is not flat. You are better at seeing some colors than others. You are not even an honest reporter within your own narrow band. But it gets worse. Much worse. Even the visible light that does reach your eye, what happens to it on the way down? Because that light does not travel from the star to your retina in a clean, uninterrupted beam. It has to pass through the atmosphere. And the atmosphere is not a window. The atmosphere is a mess. Think about what air actually is. It is a thick soup of nitrogen, oxygen, argon, water vapor, carbon dioxide, dust, pollen, smoke, pollution, and whatever else happens to be floating around that evening. The column of air above your head is roughly 60 miles deep, and every one of those miles is full of molecules. Every one of those molecules can scatter, absorb, refract, or redirect the photons coming from that star. This is not hypothetical. You can see it happening. That is why the sky is blue. Blue light has a shorter wavelength and gets scattered more by air molecules. So sunlight comes in, the blue gets scattered in every direction, and you see a blue sky. But this same scattering affects starlight too. Some of the star's blue light gets scattered away before it reaches you. The star looks slightly redder than it actually is. Not by a lot, unless it is near the horizon, but the effect is always there. The atmosphere is already lying to you about the star's color. And then there is twinkling. Stars twinkle. Everyone knows this. Most people think it is charming. Astronomers think it is a disaster. Twinkling is not some feature of the star itself. The star is not pulsing or flickering. Twinkling is the atmosphere jittering the light around. Pockets of air at different temperatures have different densities, and different densities bend light differently. So the starlight wobbles and shimmers as it comes through these turbulent cells. The image dances, the brightness fluctuates, the color shifts slightly. You are not seeing the star pulse, you are seeing the atmosphere tremble. Professional astronomers call this effect seeing, which is beautifully ironic. They measure the seeing conditions at an observatory. Good seeing means the atmosphere is relatively calm, and the star images are tight and sharp. Bad seeing means the atmosphere is churning and everything is smeared out. They build telescopes on mountaintops and deserts, on volcanic islands, and eventually in orbit, all trying to get above or away from this mess. Because the atmosphere is not just between you and the star. It is actively interfering with the signal. It is an editor, and not a gentle one. The atmosphere also absorbs certain wavelengths entirely. There are bands of infrared that water vapor blocks completely. Certain ultraviolet wavelengths get eaten by the ozone layer. The atmosphere has holes and walls in its transparency, And those holes in walls determine which parts of the star's message get through and which get swallowed before they ever reach the ground. You are not just seeing through a dirty window, you are seeing through a window with opaque patches. And there is one more thing the atmosphere does that is easy to overlook. It smears the star's image. Even if the atmosphere were perfectly still, your eye has a finite aperture, the pupil, and any finite aperture produces diffraction. The light spreads out slightly. The star, which is actually a huge ball of gas millions of miles across, appears as a dimensionless point of light. It has no visible size, no disk, no shape, just a dot. Think about how bizarre that is. The sun is a star, and it appears as a disk in your sky, because it is close enough for your eye to resolve its angular size. But move the sun to where Vega is, 25 light-years away, and it shrinks to a point. Your eye cannot resolve it. The star becomes geometry's fiction, a point with no dimension. Everything you know about a star, its size, its temperature, its composition, has to be extracted from that single unresolvable dot, from the brightness of the dot, from the color of the dot, from the way the dot wobbles or dims over time. All of stellar astronomy is built on squeezing information out of objects you literally cannot see as anything other than geometric points. And yet, from those points, human beings deduce that stars are suns, that they are made of specific elements, that they have life cycles, births and deaths, that span billions of years, that they manufacture the heavy elements in your body. All of that from unresolvable dots of ancient, filtered, grayscale light. When you think about it that way, the achievement of astronomy is almost absurd. It is like reconstructing an entire symphony from the sound of a single muffled note heard through a wall. And yet we did it, not because we see well, but because we think well, because we refuse to accept the dot as the final answer. So the atmosphere and your own optics conspire to give you an image that is smeared, jittered, color-shifted, and dimensionless. That is your raw data. That is what you are working with. And your brain says, yep, I can work with that. So let us take stock. The light is old. The light is a thin slice of the full signal. The atmosphere has filtered, scattered, reddened, jittered, and partially absorbed it. And we have not even gotten to your eye yet. Your eye. Let us talk about your eye. Because your eye is going to turn out to be much stranger than you expect. Light enters through the cornea, which is a curved transparent layer at the front. It gets partially focused. Then it passes through the pupil, which is just a hole in the colored iris that controls how much light gets in. Then through the lens, which does the fine focusing. Then through the vitreous humor, which is basically a blob of clear jelly that fills the inside of your eyeball. Then finally at the back of the eye, the light hits the retina. The retina is a thin tissue, about as thick as a few sheets of paper, and it is covered with photoreceptor cells. These are the cells that actually respond to light, and they come in two types, rods and cones. Cones are for bright light. They detect color. You have about 6 million of them, and they are concentrated in a small central area called the fovea. There are three types, one most sensitive to red light, one to green, one to blue. Your entire experience of color comes from comparing the signals from these three types. Every sunset, every painting, every rainbow is built from three overlapping channels. Just three. Rods are different. Rods are extremely sensitive. They can respond to a single photon under ideal conditions. A single photon. That is as sensitive as physics allows. But rods do not detect color. They see the world in shades of gray. And you have about 120 million of them spread mostly across the peripheral retina outside the fovea. When you go outside to look at stars at night, here is what happens. Your cones, the color detectors, need a lot of light to function. Stars do not provide enough. So your cones are essentially asleep. Your color vision is off. You are relying entirely on your rods, which means you are seeing the night sky in grayscale. That star might be a brilliant sapphire blue, telling you it is a young hot star burning at 30,000 degrees. It might be a deep ember red, an ancient giant with a surface temperature of 3,000 degrees. But you cannot tell. Not at night. Not with your eyes alone. You are seeing gray dots. And by the way, it takes time for your rods to reach full sensitivity. When you first walk outside from a lit room, you are practically blind. Your pupils dilate, which helps, but the real change is chemical. The rhodopsin molecules in your rod cells need to regenerate after being bleached by bright light. Full dark adaptation takes about 20 to 30 minutes. During that time, your sensitivity increases by a factor of roughly 1 million. 1 million. You go from nearly blind to astonishingly sensitive. And most people do not have the patience to wait for it. They glance up for 30 seconds, see a few bright stars, and go back inside. They never experience what their eyes are actually capable of. Even when fully dark adapted, you face a fundamental trade-off. Your rods are sensitive but imprecise. They have poor spatial resolution. They are spread across the peripheral retina in a coarse mosaic, not the tight, sharp grid of foveal cones. So your night vision is blurry and gray. You are trading sharpness and color for sheer sensitivity. The universe is sending you a detailed message, and your receiver can only hear the loudest parts in monotone. There is a subtlety here worth mentioning. As your eye transitions from cone-dominated daylight vision to rod-dominated night vision, something called the Purkinje shift occurs. Your peak sensitivity slides from yellow-green, where cones are best, toward blue-green, where rods are most sensitive. This means that at twilight, when both systems are partially active, the relative brightness of colored objects changes. A red flower and a blue flower that look equally bright in daylight will appear different at dusk. The blue one will seem brighter, the red one will seem to fade. This shift is named after Jan Purkinje, who noticed it in the early 1800s while walking through his garden at dawn. The flowers seemed different from how they looked at midday. He was not imagining it. His visual system was literally switching hardware, and the two sets of hardware had different sensitivity curves. The world looked different because the detector changed, not because the world changed. Your eyes do this every single evening and every single morning, and you probably never noticed. The universe stays the same. Your perception of it drifts as your biology switches modes. One more way in which seeing is not the clean, direct thing you assume it is, and it gets stranger. Remember the fovea, that central area where your sharpest daytime vision lives. The fovea is packed with cones, but it has almost no rods, which means at night the center of your vision is nearly blind. Try this sometime. Go out on a dark night, let your eyes adapt for 20 minutes, and look directly at a faint star. It will disappear. Now look slightly to the side. It pops back into view. You can see the star with your peripheral vision, but not by looking straight at it. Astronomers have known this trick for centuries. They call it averted vision. You see the star better by not looking at it. Think about what that means. The most direct, head-on, stare-at-it-hard approach to seeing a star actually makes it vanish. The best strategy is a sideways glance, and you call this seeing. But we are just getting started with the weirdness inside your eye, because the photoreceptors themselves, the rods and cones, are facing the wrong way. In the vertebrate eye, the photoreceptors point backward. They face the back of the eyeball, not the incoming light. The light has to pass through several layers of neural tissue, blood vessels and supporting cells before it even reaches the light-sensitive parts of the rods and cones. It is like building a camera and putting the film in backwards behind a layer of wiring. Every engineer who hears about this design for the first time thinks it is a joke. But evolution did not ask an engineer. It worked with what it had. And what it had is inverted. Those neural layers I mentioned, they are not just passive wiring. They are active processes. There are ganglion cells, bipolar cells, horizontal cells, amacrine cells, all forming a complex network right there in the retina. This network does not simply relay signals. It processes them. It enhances edges. It suppresses uniform areas. It detects motion. It adjusts for contrast. It compresses the data. By the time the signal leaves your eye,